Hey guys, Jay from RS Garage. We're back at Advanced Cylinder Heads doing part 2 of what to expect when you drop your engine off at the machine shop. And this section of the video is going to follow the cylinder head through the process of being refurbished, blueprinted, and ready to go back on the engine. As the cylinder head moves into the hot tank, there's some disassembly work that happens and some more problems unearth themselves. So on this first lobe, there's some abnormal wear where you can catch it with your fingernail on the lobe. So this camshaft can be polished or replaced. As you move to the second journal, both the second journal on the camshaft and the second journal in the cylinder head don't look good. So there's material transferring from the head onto the cam, and then taking the rocker arms out and spinning the rocker arms, we have a rocker arm that is really gritty. So this happens when you have the valve train floating and there's needle bearings in here and they get staked. So the pressure is enough that it jams the needle bearing into the roller and or the shaft, and then it starts to eat itself. So we're gonna knock this thing apart and show you what it looks like inside, but this rocker arm is ruined. The cylinder head, there'll be some buffing there with some Scotch-Brite to see if that will clean up, because anytime you get into having to align bore a set of cam journals, like on this, it's a bit of a troublesome mess because you shrink down the housing bore for the cam seal and it becomes a pretty thick repair. So again, you bring your stuff to the machine shop, they're gonna find things that you didn't find when you took it apart, and they're a partner in your rebuild. A good machine shop is your partner. You're gonna have multiple sets of eyes on your parts, and those multiple sets of eyes may find things that you may have missed, and these are all leading to the successful rebuild of your engine. So be fortunate to have access to good guys, because they're gonna be on your team as you go through the rebuild process. We're back at ACH and we're taking a look at Tim's Evo engine project. So like I said before, we're going to follow this engine all through the process of machining, and now it's time to do valve train. So the engine previously had Ferrea valve train in it, and that's what Tim wanted to stick with. So we've got a new set of valves, guides, seals, springs, spring seats and retainers, locks, ready to go in the head. And as they go through the machining process, we'll talk about their individual roles in the success of the engine. So we warm the head up in the parts washer to around 150 degrees, and the aluminum head will grow more than the bronze guide. And what that's going to do is loosen some of that interference fit between the cylinder head and the guide, because you're going to push that guide out to replace it. And the tighter that guide fits in the head, the more likely it could be to drag material or damage the ID of the bore that retains the guide. And if you get a scoring in that cylinder head in that area, you can create some pretty odd oil leaks where you'll have an engine that's smoking because there's oil seeping between the actual OD of the guide and the ID of the cylinder head. With the guides pressed out, you can examine the OD of the guide and you can see some abrasion or drag marks as it's pushed the guide out of the head. There's a 1 to 2 thousandths interference fit, so the guide is 1 to 2 thousandths larger than the head, and that's what keeps the guide in place and keeps oil from seeping between the cylinder head and the guide itself. Next, Brett is going to brush those guide bores, wash the head again, and we'll be ready for our new guides. With the old guides out, the cylinder head is put back in the parts washer to be heated back up to around 150 degrees. From there, they'll take the head and they'll put it on the table. They'll take the guides and they'll freeze them in liquid nitrogen, which is around -300 degrees, and then drive the new guides into the head. The reason why they don't use an oven is there's some risk and liability in heating that head up too much, where it can change the relationship between the valve seat and the casting itself, because again, that's another interference fit. So the guides are chilled in liquid nitrogen, driven into the head, but then they'll be prepared for sizing so they fit your new valve stems correctly. Next up is sizing the guides. Whether you're pushing the old guide out or pushing the new guide in, you change the ID of the guide slightly. So even though you bought new valve guides, you're still gonna have to size the ID of that guide to fit the valve stem correctly. This is a guide reamer, so this is gonna go down through the guide and create a straight guide, because remember, when you pushed the guide down into the cylinder head, you changed its shape some. From there you move to a hone. So this is kind of similar to your cylinder bores, where you have a bore and hone job, and you'll hone the guide for the correct clearance between the valve guide and the valve stem. With an older style approach like I just showed you, you can have a decent outcome with an experienced machinist and a lot of time invested in doing the job right. Because remember, you're dealing with an engine that has 8 valves, 16 valves, 24 valves, 32 valves, 48 valves. And each individual valve is an opportunity to have a better engine or an engine that can have a potential problem. Here at ACH, they have a CNC guide hone, so you're going to be able to get each individual guide straight and true and set the correct clearance in a timely manner, providing for not only a shorter amount of time behind the machine doing the work, but a better finished product. In the final strokes, the machine is going to be applying a crosshatch inside of the guide. Even though a bronze guide doesn't need a lot of oil because it's self-lubricating, having the crosshatch there is important, and the machine creates a repeatable finish from guide to guide. So as the machine goes through its paces of straightening the guide and setting the clearance between the guide and the valve, let's talk about how that's affected an engine operation. So when you have an engine that has a bucket design where the camshaft rolls over a bucket and opens and closes it like a 2JZ, there's very little room for side loading at the top of that valve, in that the valve is free to go up and down in the guide. When you get into an engine like the 4G63, where there's now a lifter and a rocker arm, there's some amount of geometry that's going to be side loading that valve. It's not gross, but it's present. And then if you get into worst case scenarios, you're talking about aftermarket V8 engines, pushrod engines with aftermarket cylinder heads and aftermarket rocker arms, and getting the valve train sorted on one of those engines where the valve guides can experience a full life cycle is quite challenging. Not impossible, but quite challenging. So if you are working on a Japanese engine, like this one here, it's pretty easy. Once you get all this stuff right and you're ready to move forward with your project, aside from tuning air shoes, you can have a pretty awesome engine. With the valve guides honed, it's time to surface the cylinder head. The valve job machine is going to indicate off the deck of the head, so they need to make sure that the deck of the head is completely flat. So indicate the cylinder head in the machine, make sure it's flat, give it a quick haircut, over to valve job. With the head in the surfacer, you're looking to get the cylinder head flat again, so you have good gasket retention. And taking a thousandth off the cylinder head has material off this end of the cylinder head and this end of the cylinder head, but barely touching this corner and not touching that corner. So the head has a bit of a twist to it that taking a thousandth off really shows that. As we move towards the valve job, let's talk about how the valve job interacts with the engine's ability to pump air. The valve job is going to seal the valves into the valve seat. And while that's important that there's not air leaking past the valve, it's also critically important that as the valve is laying on the seat, it's exhausting heat from combustion back into the seat. So the valve is not only sealed through the valve job, it is also cooled through the valve job. And over the years, there's been many ways of doing valve jobs. If you go back into some early stuff, you have stones that are cut at angles. So you cut the valve on a machine like this, and then you cut the seat with a stone, and then you do some hand finishing to make those interact well. Things advance a bit, and you get into fixed cutters that will locate in the valve guide and cut the valve seat that way. You get a little bit more exotic with some other style cutters, again, fixed point cutters. And then you get into something like the Newen machine where that cutter is in a dynamic state as it moves from the valve seat out to the end of the valve job. So multiple angles are created as that happens, and the repeatability between valve and seat is excellent between valve to valve to valve, because if you have a 24 valve engine or a 16 valve engine, you have 16 or 24 different opportunities to have a problem. And the more advanced that machine is, the better it can create a finished product with the least amount of man time. So it's all about not only the best finished product, but managing man time, which then manages costs back to the consumer. So right above my fingernail is the contact angle. That's the area that's going to actually make contact and seal the valve. So we're going to widen that up a little bit because it is a turbo application. And even if the valve has a little bit less flow, we'll take the durability. If you're wondering why we're modifying a brand new valve, this is the margin or width of the valve job. So that right there is the amount of valve that's going to be contacting the seat, allowing the valve to seal and allowing the valve to transfer the heat that's in the valve down into the seat to be carried away from the valve. If we look at a modified valve that we're going to use, we have a much wider valve job. Now, this isn't going to perform as well on a flow bench, but what do we care about a few CFM? We're dealing with a boosted application and we want longevity. This is one of the coolest machines in the shop. This is a new CNC Valve Job machine. So it's got a single point cutter that has basically an infinitely adjustable plot to it. So you can prescribe from the bowl out into the chamber, whatever shapes you like. And it's really wild to watch it in motion. Valve job's complete, cylinder head's been deburred and washed. And now it's time to measure installed height and start to reassemble the head. Now the installed height is going to be the height that the valve spring is installed at. So from the cup to the retainer, what is that distance? And that distance is going to affect how much pressure is on the spring when it's in its closed position. Now, you have 16 valves on the cylinder head, and the idea is to get all of the valves at the same installed height. That way, all of the valve springs are doing the same amount of work. It also gives you an opportunity to make sure that you're not getting an error in the parts you've ordered. Now, this is an old school installed height checker. So on a conventional 2-valve pushrod engine, there's a lot of room. You put this tool in here, you open the tool up, you read the side of the tool, it gives you the installed height. Because you don't have the real estate to use a big tool like that in the cylinder head, going to install the valve into the cylinder head, check and see the valve tip height from the spring seat to the tip of the valve, and then install the locks and retainer onto the valve, and then do some math. So we'll measure the distance from the tip of the valve to the bottom of the retainer, and then from there we know, because we have a valve tip to seat measurement, what our installed height is going to be, and we can work through getting all 16 of these valves in the right place and knowing how the springs are going to behave in operation. Now that we know our installed height, we can go ahead and take that information and plug it into this. It's basically a valve spring dyno, a really handy tool. And we set our installed height, we know the max lift of the cam, and we can basically dyno the spring to know what our seat pressure is and our open pressure. So the seat pressure is going to be the amount of pressure on the spring before the camshaft actuates it, and the over the nose or open pressure is at max lift. This will also tell us how far we are from coil bind, and that's when this valve spring stacks up on itself. You don't want to run a valve spring into coil bind. You want to have some cushion. Now, you don't want to be too far away from bind because then the spring can pick up some noise. So there's some limitations there and some rules, but we're going to get into that into another video. For now, we need to know what it's going to take to get this valve spring to be able to perform accurately. And Freya's looking for around 90 pounds on the seat. And we are around 90 pounds on the seat once we install a 60,000 shim under the locator. And that's because this cylinder head's been worked on. So every time you valve job a head, the valve goes a little bit further up in the head, which increases the installed height because you're moving those components around. And this is why it's important to check and to know. The guys that tear up valve train parts, maybe they're lacking this information or lacking this setup. So just because you bought a set of valve springs, you put them on in your driveway on a Saturday, you may be better off, but you're probably not optimized. Another thing to consider when you're blueprinting valve train is the amount of variables that you have. So this is a 4-cylinder engine with a 4 valve per cylinder. So you have 16 valve springs and they're dual, so now you have 32 valve springs. And all 32 of those valve springs are variables. And if you have a situation where you have a problem on one cylinder, wouldn't you like to know that all of the valve springs were equal the day of installation? So you can go through and check every spring as a pair, and if you needed to, you may take an inner spring out of one and pair it with an outer. But as we went through and checked all these Freya springs, they're all within a couple of pounds, which is pretty awesome pairing on their part. As I mentioned before, the cylinder head's been valve jobbed more than once, and every time you cut that seat, you effectively shift the valve up into the head. So now that the valve head is deeper in the seat, the valve tip is higher in the head. So what he's going through now is tipping the valve, which is removing or grinding a small amount off the valve tip to get it back within the factory specification. 4G63 is a hydraulic lifter with a rocker arm, but there's still a range that you want that valve tip height to be in. So we knew where the valve tip was, we know what the factory specification is, and the fix to get it within spec is just grinding the tip of the valve. Before we put the head together, this is a good opportunity to show you how the locks work. So here's your valve, here's your retainer. Drop the retainer down onto the valve, and then you have these 2 valve locks. Now the ID of this hole is cut at an angle, and the OD of the lock is also an angle. So there's a small raised radius that's going to protrude into the groove on the valve. So one lock goes on, the other lock goes on, and as the retainer slides up, it holds the valves in place. Now, retainers, locks, valves, throughout different manufacturers and OEM stuff, you can really cause some havoc here if you have a mismatch of parts. So it's best to take a real close look at how the locks and retainers and valves interact with each other, because you don't want to put it together, have it wrong, and then have a valve go into the cylinder. We're pretty close to a finished cylinder head. The last step we have is to put the oil galley plugs back in. Some cylinder heads have screw-in plugs, others have balls. It's common practice to take the balls out, tap the cylinder head, and use plugs because you want to get all those oil galleys completely clean. If you had an engine that lost a bearing and they're pushing particulate through the engine, it hides in these places, and you want to make sure that it's not going to contaminate your new engine. So all the plugs were removed from the cylinder head during the cleaning phase of it, and now that the valve train is installed, we have to do the plugs. Then we can put the new lifters in, new camshafts in, rocker arms, but I'll do that once it's on the engine. With the cylinder head work completed, it's time to get this thing bagged up and get it back to the shop. However, I want to protect the deck during transport. So I'm going to take a piece of cardboard, I'm going to cover the deck, wrap it in plastic, then put it in a bag. You don't want to have any damage on the deck of the block or the deck of the head because you can render a part useless. So very careful in transporting these components. You don't want metal things banging against other metal things, and you want to make sure the deck surface is protected.